I'm from the Department of Bioproducts and Biosystems Engineering at the University of Minnesota. I'm not a native Minnesotan. I'm from upstate New York. I've been in Minnesota at the university since 1985, so I guess I'm a Minnesotan now. I don't know if I have the accent or not. I did spend 6 years in Texas, so I have a real issue about accents. Because you go from New York, where you have no accent, upstate New York, where you have no accent, to Texas, where you have a strong accent, and to Minnesota, where they say you have a strong accent as well. So I make fun of my wife, who's from St. Paul, you know, with her accent. Anyway, so we had this project that was actually the brainchild of John Gulliver, one of the co-PIs on the project. And we had discussions with the Watershed District and with MWML about funding this project, and we did get it funded. And I'll go through and talk about what the background is for it. I don't know what everybody's backgrounds are. Leslie sent me a list of who was going to be here, so I'm going to try my best to convey the information in a way that's not too technical. I know some of you are from consulting firms, some from agencies, and so forth. I'll try to present in a way that is not too technical, so that it's understandable what we did. We used various methods to study the base flow, chemical methods, hydraulic methods, and so forth, hydrologic analyses, and I'll just try my best. And so what I would like to do is, Leslie said I have an hour, but I don't want to wait until the end before I get questions. So if you have questions that need to be asked during the presentation, please ask them, because that way I can answer them at that point. You don't have to try to remember to ask at the end of the presentation. So feel free to say something, raise your hand if I'm not looking at you, and go ahead, and we can try to address any questions you might have. Other people working on the project were, as I say, John Gulliver was the co-principal investigator, Joe Magner, who was with the MPCA for 30 years and is now retired and working at the University of Minnesota as a full-time researcher and teacher. Ryan Berkemeyer is a graduate student in water resource science at the university. And then Tricia Moore, who is a postdoc on the project, and she's recently, in November, left to take a faculty position at Kansas State University. It says AGU fall meeting. Well, I just forgot to change that part of the slide, because I made this presentation at the American Geophysical Union meeting. A much shorter version, because they only give me 12 minutes to give those presentations, so much shorter version than what I'll be talking about today. So the issues that came forward was, of course, everybody knows that every once in a while Minnehaha Creek dries up, or it gets very low flow, especially when the gate at Lake Minnetonka at Grays Bay is closed. And so the issue comes up, is it possible that we can augment that base flow in some way? We know that there's a lot of stormwater that's generated in the watershed, and so the question would be that we wanted to try to address was if we infiltrate additional water into the soil, to the superficial aquifer, will that water end up coming into the creek? Because it will. There's quite a bit of water in that stormwater, and right now it just runs directly to the creek. It raises the flow in the creek, up like this, and it'll come back down very rapidly. So it's a very flashy type flow. If instead of just allowing that to happen, if we run it through the soil, through the groundwater system, maybe we can reduce the flashiness of the creek, and that would help with some of the aquatic habitat, because you don't get things washed out. But also you'd be treating the water, because there are impairments in the creek that have to do with not just the low flows, but temperature of the water, as well as chemicals that are in the stormwater. So if we can run that through the soil, through the groundwater, maybe it can actually help to improve the quality of the water in the creek as well. So does any of that extra water we add to it, if we were to add extra water, by infiltrating that stormwater in rain gardens and those kind of features, would that water end up in the creek? And so our objective then was to try to determine that by trying to better understand the hydrology in course, I probably don't have to tell you some of the things around here. The people at the AGU meeting, I had to tell them because they know nothing about the Minnehaha Creek. But of course, we know that it's an important feature here in the Twin Cities metro area. The creek is visited, the park is visited by many people every year. Then the layout, of course, is shown here. You've got the lower part of the watershed that's has an input from the upper watershed at the Grays Bay. The upper part of the watershed is about 123 square miles. The lower part of the watershed is 50 square miles. Minnehaha Creek exists in the lower part of the watershed. Of course, over on the right-hand side, you've got Hiawatha Boulevard. That's right, I can't show it with this thing because it doesn't show up on a screen. But if you watch the cursor, you know, we have Hiawatha Boulevard over here, a little bit upstream of that point. Of course, the falls is located there, and the Mississippi River is running right along that lower end of the creek. Grays Bay was put in about 1892 or 1897, somewhere around there, and has been there to help control the flows in the creek and, of course, to control the water levels in the lake. And this is in a photograph. Many of you have probably been to the site to look at the dam at Grays Bay. The district monitors the flow, or monitors water levels on the upstream and downstream side of this dam, so we're able to calculate what the flows are that are going through the dam at any given time. And that, of course, is important for us to be able to do our water balance calculations that I'll be talking about. We need to know how much water is flowing through the dam at the upper end. Well, for the period of record, which is the last 13 years or so, almost 14 years of flow record that have existed for Minnehaha Creek, there have been 9 dry periods during that period of time. So that's quite frequent to have that occur. And what's shown here is a flow duration curve. Yes?
So apparently, I think is there a tan, somebody with tan Honda with Wisconsin plate parked along the side here. You lost, and then an olive truck. There's a shipment that's coming in from our neighbor next door, and they can't get the truck in.
Can we park in the MCWD vehicles only park?
You absolutely can.
Okay.
Sorry about that.
Record what I missed.
It's being recorded, from what I understand.
Oh, it is?
Yeah. So this is a flow duration curve, which illustrates the duration magnitudes of flows. And I'll just come over here since I'm not able to use the cursor. Hopefully people down on this side can see it. But each one of these curves represent the magnitude of the discharge that's equaled or exceeded a certain percentage of time. And so the very high flows in the creek, of course, occur just very brief periods of time. On the horizontal axis, you have the percent of the time that that particular flow is exceeded, that the flow in the creek is greater than that value. So, of course, the very high flows are going to have a very small percentage of time that that flow is exceeded. The very low flows are going to have a large period of time that those would be exceeded. And I think mainly what this diagram is supposed to, why we put this up here, and these would be for different seasons. So we take the flow record for different seasons, summer season, fall season, spring season, and we draw this or make this calculation to come up with this plot. And what we see here is that there's quite a high frequency of time when the flow is less than 1/10 of a cubic foot per second. So for the fall season here, it's about there's about 15% of the time that you don't have any flow in the creek. In the summer season, it's almost 28% of the time. So that's quite a long period of time for aquatic organisms to exist in the creek, maybe just in pools if they do exist, when there is no flow in the creek. And that's, of course, going to be somewhat harmful. The other thing that's listed on here is the flashiness index, which is an indication of how rapidly the flows change in the creek. And the number here is about 0.5 for the creek. That's not necessarily represented by the flow duration curve, but it would be represented by hydrographs, which I thought I had in my slide presentation. But I guess I don't have it in here. But the flows become, they change very rapidly. This flashiness index is rather large if you compare it to a lot of other watersheds of the size that Minnehaha Creek is. You might expect it to be more on the order of about 0.25. And I think probably that is largely because of the stormwater that we have coming into the creek is the reason for that high flashiness index. So the creek itself suffers a number of flow-related impairments besides the chemistry of the creek, but there's also just these very rapid changes in flow and then a long period of time when there is no flow. So there was a TMDL, of course, that has been conducted for the creek, and one of the things that shows up is that the reason for the impairment or the aquatic impairment, biotic impairment for the creek is because of low DO, warmer temperatures, and then also because of the low flows that occur. And of course, here I've got a picture of Minnehaha Creek with no flow, or the falls with no flow going over it. And we came across this newspaper article from 1892 when President Benjamin Harrison was here for the Republican Convention. And he stated that Minnehaha Falls would undoubtedly look very nice. It would be very beautiful if there was water in the stream. So apparently at the time when he was here, there was no water in the stream.
And the weir was present by then, or not?
The weir was right around that time was put in. I think this might have been just prior to that, but I have to go back and check my records. It was somewhere around 1892, 1894 that it was put in. Might have been as late as 1897, actually.
What would account for that without the weir? The stream was dry when it was there.
Well, there's just not enough flow going in. So is this event, this observation that he made, something that occurred a lot back then, and maybe there's nothing you can do about what's going on now?
And do we know any?
We've been trying to find out, but there's no witnesses around. So, I mean, can we come up with more newspaper articles that would say something about that? And we haven't come across that yet. So I've been begging people to tell me if they know of something. So, 18. Yeah, I think this. I believe it was after this occurred. Yes. But so I mean, it wouldn't necessarily the weir wouldn't necessarily. Well, I mean, it stops the flow coming out of the lake at a certain level, right? I don't know what their release criteria was at that time. We know why there's a certain criteria now. They want to maintain a certain water level in Lake Minnetonka. Whether that same water level was desirable at that time, I have no idea. So I don't know what their operation of the weir was when they first put it in. So now if you stop the flow coming out, I mean, at some point, there'd be no water coming out whether there's a weir or not. If the water level in the lake gets low, like White Bear Lake, well, then there wouldn't be any water coming across there anyhow. But as it is right now, the water level, or that weir is usually closed before it would get to the point where there'd be no flow coming out of the creek, or coming into the creek. I think anybody that's visited the park, of course, has seen this picture that's posted there right near the falls. Shows President Lyndon Johnson and Hubert Humphrey having a good laugh. This is 1964, and of course at that time the flow, when there was flow over the falls, 6 million gallons of municipal water was released to make the falls flow, because again it was a time when there was a dry period. So that was their fix to make the creek flow. But the proposed new fix, which we were working on, was to reroute stormwater. Because the district not only wants to clean up the water by trying to control that stormwater. You know, if we can infiltrate it in strategic locations in the watershed, maybe we can actually augment the stream flow. So if we were to take all that stormwater and spread it out over a longer period of time, it might be that we can actually augment the base flow. That's the idea behind that. And this just illustrates all the impervious areas in the watershed. You can see that a lot of the impervious is in the middle part and the lower part of the watershed. There's some also in the upper part as well, but it's less dense. So these would be places where we might be able to redirect flow. Okay, so the question is, I asked this question at the beginning. I said, okay, well, if I infiltrate the water, will it help to augment the base flow? That is, will the water actually make it to the creek? If it goes into the groundwater, does it evaporate back in the air if the trees and the plants take it out? If it's pumped, let's say, from deeper aquifers, does it get drawn down to the municipal wells? You know, exactly what happens to that water. And that was our objective, is to try to understand better what's going on. So that's why we did this study. And I threw this in here just to illustrate the concept of capturing the stormwater and putting it into the creek. And so this would show the runoff shed for a particular area, and the little light area that's shown along the creek there, that area would be the area that you might somehow infiltrate that water close to the channel. So you take all that runoff, put it there, and then let it seep slowly into the creek. That would be the concept. So the methods that we used were various techniques. They were based on doing water balance calculations. We used stable isotopes, basically natural tracers, to be able to quantify where the water is coming from that's entering the creek. We made measurements in the stream bed. We used seepage meters, and we used temperature profiling method. We put in our own piezometers along the creek, and then we also did hydrologic system analysis. So I'm going to talk about these individual methods, and then at the end I'm going to talk a bit about the geology and why we think things are happening the way that they are happening. Okay, well, I guess here's where I put that slide that shows the hydrograph. So talking about the water balance, you know, we take these flows in cubic feet per second over time. These would be the measurements at Hiawatha Boulevard down in the lower part of the park. And what's illustrated there, the blue line is the flow at Hiawatha Boulevard at the U.S. Geological Survey gauge there. And the red line is the flow that's coming into the creek from Grays Bay. And the kind of the flat part of those Grays Bay calculations, well, it's coming out of a big reservoir, so it's going to be more smooth or more steady type of outflow. But these were numbers, figures that we had early on, and we've actually made corrections to the calculations that we received from the district, because there's some things about the rating curve that had to be taken into account. So the red line is a little bit modified to what is shown here, and I haven't gotten that onto the graph yet. We've got the precipitation events that are occurring. This is from February 12, 2012 till October 2013, the period of our study. And you can see the precipitation events and how the runoff is related to that. And you can see the flashiness, you know, the highs and the lows in the flow. They're very rapid as far as the stream flow is concerned. That's how I got that flashiness index value to be so high. Okay, so we did the flow calculation just to give you an appreciation for the volumes of flow. And I was told by James Whisker, you know, when I make the presentation to the district board a couple weeks ago, or a month ago, I should use acre feet, because people might have a good feeling for what acre foot is, right? So it's an acre of land with 1 foot of water on it. That's a acre foot. So the flow coming out of Grays Bay on an average annual basis is 20,000 acre feet. Flow that's just stormwater that's from the lower part of the watershed, just the stormwater component, It's about 5,000, a little over 5,000 acre-feet of water. And then base flow, which should just be the low flows, not necessarily groundwater flow. Base flow is about 4,000. So if you look at the contribution to flow here, 70% is from Graves Bay, and the remainder is from the lower part of the watershed. So only about 30% is coming from the lower part of the watershed. And what else? Yeah. This is the period of record that we have flow. You know, so that about 1999 until present. These calculations were done up through last fall. The annual precipitation is about 32 inches, so you can relate that. These would be the equivalent depths of water that would be on the surface of the watershed. So, you know, about a couple inches of water is coming out of the watershed from the lower part of the watershed. Out of 32 inches, only about 3.6 inches actually makes it to the outlet. The rest of it's evaporating away or going somewhere else. All right, so that's gives you, I hope, gives you an appreciation for the magnitudes of the flows. So the question is then, or one question is, where's the water that's in the channel coming from? Well, we know how much is coming from Grays Bay because we've got a gauge there to make that measurement. But the flow that's coming into the watershed, into the creek in the lower part, how do we quantify where it's coming from? We want to know how much is surface runoff, how much is coming from groundwater, and how much might be coming from the lakes and wetlands, like the chain of lakes, Lake Harriet and so forth. How much is coming from the little wetlands and so forth, and how much is coming from groundwater. So we used a stable isotope method to do this, and stable isotopes are basically ways of quantifying the difference between the source waters, what's generating the flow. So how much of it is coming from Lake Minnetonka? Well, we already know that. How much is coming from the chain of lakes? That's something we don't know because we have no gauge to measure that. How much is coming from wetlands that are near the channel, and how much is coming from precipitation and runoff? I don't have a picture of groundwater here, but that would be the other possible source. Well, what we know is if we go and we measure the chemistry, the stable isotope content of each of these sources of water, they are distinct from each other. So if we have all of them contributing in some way, the final content of that isotope, we can find out, okay, how much is coming from each of those sources just by proportion. It's a fairly simple algebraic calculation that you need to do. So we are using the stable isotopes of oxygen and hydrogen to do this. We could use chloride. There's a lot of other types of chemicals that we could use. And this just illustrates where we made these measurements. We made some of the measurements in lakes and wetlands, and made some of the measurements in the creek, wherever you can see the star. We would do these during storm flow events, during low flow events, and so forth, so we could get a record of how things changed over time. And we also made measurements in the riparian aquifers and some of the deeper aquifers as well. So we're able to quantify what the isotope, the chemical content of each of those sources is. So we've got a signature, a chemical signature for each of those sources. I'll try to illustrate that here. We also took samples of snow, so we'd know what the isotopic content of the snow is. So on this axis we have the, we'll just say that it's relative concentration of the oxygen isotope, and on the vertical axis is the relative concentration of the hydrogen isotope. This is deuterium, and this is you know, important in atomic bomb making, you know, deuterium. And then this is oxygen isotope O18. The normal oxygen atom is molecule is O16. All right, so what we see here is that the chemistry for the snow melt falls down in here for these two chemicals. They fall down, it falls down in here. For the aquifers, it's these blue diamonds, and these were for different seasons. So the summer during the drought, the groundwater part fell within there, and also the during the spring snow melt and during the summer period, they all fell within this range here. These are the headwater aquifers. So it's fairly narrow range that the chemical signature for that for groundwater is stable. And then for lakes and wetlands, they fall up in here. So all I want you to get out of this is that the chemistry of the lakes and wetlands falls up here. The chemistry of the snowmelt falls down in here. So now if I take each of those sources and mix them together in any particular event, I can partition out based on the knowledge that this is the basic signature for each of those chemicals. So we measure a flow at Hiawatha Boulevard, all right, and I can then say, all right, well, this fraction, because I measure the chemistry of that water as well, I can now separate out that flow into these different components based on those chemical signatures.
What about the non-snow precipitation? Yeah, the non-snow precipitation.
That is right there. And that does vary. Just it depends on where the water's coming from. Gulf of Mexico, from Pacific Northwest, from cornfield in Nebraska, you know, because of evaporation off that. So that does vary. And it turns out that the groundwater is generally somewhat of an average of that over the on an annual basis, because you get it's a big storage mechanism. So I would go out when we had a big storm event out on my porch, and I would catch the rainwater, and I would take that sample in. This is to get the chemical concentration in that. And then either me or my people worked with me, Tricia or Ryan would go out and they'd take these samples out of the creek and so forth whenever those things occurred. We just wanted those big events, you know, so we'd go out and do those samplings. This then illustrates how this works. Here's the actual concentration of the chemical in the stream water, and this is during the snowmelt period, so we expect it's going to be dominated by snow. I've also got superimposed on here the values that were on the previous graph. And then as the season goes on, the chemical concentration starts to look more like, see, here's the triangles, which are the flows, the concentration in the creek, starts to look more like the lakes and the wetlands. All right. And, you know, in between here, I mean, there are no triangles in here. Well, it's not dominated by the groundwater, and we'll see that in the final result. But basically, I would take any one of these numbers, the values that are given here, along with the flow, and I could separate that out. How much of it is groundwater, how much is surface runoff, how much of it is from Lake Minnetonka, and so forth. The final result, then, is this. I'm able to take the flow, and this is just a section from May until August, and this is totally wrong. This happened last time, Leslie, when I gave the board presentation. If I put this on my computer, this is 2012, and my wife was sitting me making the presentation, and my niece, who lives on the creek, was watching it too as an interested party. She said, how come you did the study in 2012 and 13? It says 2008. And I said, no, I couldn't have been. And I looked at it, it's supposed to be 2000. So somehow your computer changes it on me. I don't know what's going on.
The slide says 12, I mean the paper says 12.
Yeah, on the slide presentation it says 2012. Anyway, this is the actual hydrograph. This is the flow at Hiawatha Boulevard that's measured. We took what's called a Baseflow filter that would separate out this hydrograph into direct runoff, which is the difference between the red line and blue line. You can think of that as being surface runoff. And this is what's considered to be baseflow, not groundwater. You got to be careful about that. This would be flow coming from the lakes, you know, from Lake Harriet, Lake Minnetonka, ponds and wetlands, and so forth. Using the isotopes, we're able to separate out the groundwater component, which is just this teeny amount down here. You can see that the groundwater contribution gets smaller as the season goes on. Okay, and these numbers here just kind of give you a ratio of the flow of the groundwater to the total flow in the creek. All right. So there's about 6 inches of recharge to the aquifer. So you think, oh, why doesn't all that come out into the creek? Well, this is how much, based on this number here, this graph here. If we integrate this over time, ends up to be in 1/4 of an inch to 3/10 of an inch of groundwater coming into the creek. That's a tiny fraction of the overall recharge to the aquifer. So why? I mean, we don't know. And is our result even correct? So we needed to try to figure that out if it's correct or not. So we used some other methods, independent methods, to do the tests. And so what we did is we did these stream bed fluxes. We used seepage meters, and we used a temperature profiling method. And I'll try to go through that fairly quickly. But my conclusion that I'm going to tell you is that it's amazing how close the numbers are to what we got from the isotope, basically about 0.3 of an inch from groundwater. All right, so the seepage meter is just something that was developed, I think it was developed within the U.S. Geological Survey. They used these for the White Bear Lake study. See that these containers inserted into the sediment, and then basically any water coming into it is going to go into this bag, which you measure, or if the water is going that way, you're losing water out of the creek, the water is going to come out of the bag, and you'll be able to measure that difference. And this shows one of the seepage meters that we put in a number of different locations along the creek with the bag and the containers driven into the bed of the channel. We could only make these measurements when there was low flow, because during high flow the water's hitting the container and all that, and it just doesn't work very well. So when there's 200 cubic feet per second running in the creek, you can't do these measurements. What's shown here is how those seepage meter measurements vary, and this is for 3 different meters, and we can see that in August, this must have been in 2012, or yeah, no, it might have been in 2013, how that the seepage into the creek is varying. We can see that during a wetter period, it's rainfall period, it's high, and then as that rainfall, it gets drier, the amount of flow coming into the creek actually gets smaller. This is at a place where the creek is gaining water from the groundwater. So, and the ground, as it says there, it declined during the dry period. But basically, in all cases here, the flow was upward into the creek. To give a summary then, if you look at the whole watershed here, there are 8 locations where we made detailed measurements from the upper end to the lower end. And what's illustrated here is the flux into the creek or flux out of the creek. Wherever the numbers are above 0, this part here, the creek is gaining water from groundwater. Wherever the flux is negative, below that line, the creek is losing water. And this just kind of gives you the range of those values. If we take the average over the whole creek, it ends up being about 0.2 centimeters per day upward into the creek. That's the average over the entire creek. So there's a large portion of the creek where we're losing water. And it's mainly in the lower part of the creek. As you can see, these locations here correspond to site 1, 2, 3, 4, 1, 2, 3, 4. So in the upper part of the creek, we're gaining water into the creek. In the lower part, we have predominantly, well, on average, losing water. Okay? We also made independent measurements using temperature profile, which is a lot easier to make. Basically, you take a probe, we take a measurement near the surface, and then at 2 other depths within the profile, and we can determine which direction the flow is occurring from making those temperature measurements. In this case, the numbers on there are just made up for one of our events, 25 degrees C, 18 degrees, and 15 degrees C. And this is the probe. It's a steel probe. You can drive it into the channel bottom and make these temperature measurements with it. And so then we have a fancy equation that we put those numbers into, and the equation allows us to calculate the flux Q, whether it's up or down. And just to illustrate then, this just shows 3 different profiles that were measured. One was on the left bank, or near the left bank. One's in the very middle of the channel, or the thalweg, and the other part's on the right bank. You can see 3 different cases. This one means the profile of temperatures means that the flow is upward, and it actually ended up being 3 centimeters per day. On the other end, on the other side, it's 4 centimeters downward, and that's just based on those temperatures. What's nice about this method is that you can make lots of measurements. Send a undergrad out there, you know, and they can make these measurements all day long. The seepage meter is a lot more complicated. And so this illustrates what it looks like at one location. I think this is near the Blake Street area. Yeah. And so you can see that as you go across the channel, some places the flow is up, some places the flow is down. And yeah. Yeah. This one?
Yeah. So is this saying that the groundwater is seeping in
At different rates, at different locations. In some places it's up, and some places it's down.
So that underground spring, or?
Yeah, the flow might be concentrated in certain places because the groundwater system is very heterogeneous. There would be conduits of flow. And you might say more permeable material at some places, more porous material that would be more conducive to flow occurring. So, but and then whether it's upward flow or downward flow just depends on the gradient or the water table elevation at a given location.
And does the temperature tell you kind of the source of that underground flow?
Well, we know what the groundwater temperature is. For one thing, it's about 15 degrees C. And if we know that profile, then we're able to calculate whether it's an upward or downward flow, with that equation that I showed. Because the water is carrying that heat with it. So whether it's carrying the heat from the upper stream down or whether it's carrying it from the groundwater up, that will be reflected in those temperature profiles. And this just illustrates the profiles. I haven't been able to explain this one yet here, but this is up near the Johanna Wetland Park area. And of course, this down near Hiawatha Boulevard. But you can see in a large portion of the creek, we have a losing stream. And in the upper part, we have gaining. At least the seepage meters indicated gaining up here. This one is I'll call it an anomaly. Haven't figured that one out yet. But that's what the distribution looks like. Again, if we take the flows that we measure with this, we get about 0.3 of an inch per year. So we knew what the answer we wanted to get, so the answer came out correct. Well, hopefully it's not that way. But all right, then we also put in piezometers. And I don't want to take a lot of time on this, so I just want to show what we did. But basically, the piezometers confirmed the fact that the flows were in the directions that we were quantifying with the seepage meter and with the temperature probe. So this is at the Blake site again. This is a cold storage area that's been purchased by the district and is going to be converted into an area that we could hope we could infiltrate water. These are the locations of where we put some piezometers in along the edge of the creek. And we measured water levels in those piezometers, and wherever the water level in the piezometer is higher than the water level in the creek, that would mean that there would be upward flow or flow going from the groundwater into the creek. And so what's shown here is these X's or these stars would be the water level in the creek, and these other symbols above that would be for different wells, and of course these are for different times. And because the water level in the well is greater than the water level in the creek, that would mean that there's an upward flow. The pressure is upward into the creek. And this occurs under low flow conditions and high flow conditions. The gradient is greater into the creek during low flow conditions, which would indicate that there's some possibility of sustaining flows into the creek during low flow conditions, good base flow conditions. All right, then we also took data and did a hydrologic system model, not a complicated model at all, just something that could look at the whole watershed, do an analysis, and figure out what the properties of the aquifer are and so forth. So in the ideal situation, this is my cartoon sketch of what's going on. We have water table going down here, water flowing into the creek. The geology is such that we have Platteville limestone, which is fractured. We have Glenwood shale, which I don't believe is fractured, but it generally is considered to be unfractured. We have St. Peter sandstone, Prairie du Chien, where large municipal wells are located, and Jordan sandstone, also where we have some large municipal wells. These arrows here indicate the flow towards the creek. So we have about 6.7 inches of net recharge to the surficial aquifer on an annual basis. And this is what I was asking. Okay, well, if this Platteville limestone and the Glenwood shale are basically an impermeable bottom for the aquifer, well, all that water should end up in the creek and should come out at Hiawatha Boulevard. Why are we only getting 0.2 of an inch or 0.3 of an inch coming out? And that's well, it's because this isn't exactly the situation we have. But the this system model that we developed or worked with takes the flow in the creek and tries to quantify the characteristics of that surficial aquifer. And so we did that, taking the flow data, and this is a method that we developed back with when I was a grad student early on, many years ago. Developed this method, and you take the drought flows or the low flows, and you can take the data with this method, plotting rate of change of flow versus the actual flow, and you can come up with the aquifer properties from that, from this equation. So I won't go into a lot of detail on this, but the parameters here indicate that only about 5% of the watershed is underlain by stream feeding aquifers. Well, we know the aquifer is over the entire watershed. So why is does this method indicate only about 5% of that aquifer is feeding to the creek? So that was the next thing that we want to try to figure out. And so if I were to draw on here, well, what's 5%? Well, this is just my hand sketch on here, and that's certainly more than 5%. But what we're saying is that the aquifer, which underlays this whole watershed, only the part, if I say 5%, only the part near the creek is actually adding water to the creek. If I just spread that out over the entire creek, not the whole creek is actually receiving water from groundwater. So that's just yeah, I'm sorry I added that after I printed these out.
But maybe you could make this available to us.
Yes.
Great.
Yes. So again, this is just my cartoon sketch. I don't know exactly what 5% would be. I think that probably represents more than 5%. But just to give you the conceptual idea that if the watershed were homogeneous, the aquifer were homogeneous over the entire system, exactly 5% of it would be somewhere just basically a strip near the creek would actually be contributing. So the real question is, well, why is this? And this is the concept. Based on the geology we have in the site, that we know about the site, that these limestone, St. Peter sandstone and so on, actually were excavated out in geological time by rivers that went through. So the Platteville was eroded, the St. Peter's sandstone was eroded, so that this is glacial material now, permeable material that goes all the way right down to the Prairie du Chien. And what we're saying, instead of that 6.7 inches going into the creek, all flowing to the creek, if you have this impermeable bottom, instead what's happening is that a large portion of that is seeping down. Some of my arrows got lost off on here, but water's seeping down into the deeper aquifer. And my estimate would be, if this is how much is coming into the aquifer and we're only getting that much out of the creek, the remainder is being lost to the deeper aquifers. So let's look at this. The system is a lot more complicated than just assuming some kind of a homogeneity. So here we'll just look briefly at the geology of the area, and the question is it conducive to promoting groundwater discharge into the creek? The question is, could excessive pumping be causing loss of water that would otherwise seep into the creek? Could maybe the stormwater infrastructure be causing bypassing of flow so that it comes out of the stormwater infrastructure instead of coming out of the groundwater seeping into the creek? So we'll look at each of those here. So if we look at the geology of the area, here's the lower watershed. You can see the creek here, and this lighter area that's shown on there is that Platteville limestone. Now, under perfect conditions, that would be uniform across the entire watershed, but it's not. We can see that there are places here where it's been eroded away to expose either the St. Peter sandstone or the Prairie du Chien aquifer. Where it's kind of rusty colored, that's the where it's been exposed to the St. Peter sandstone, which I understand is shaly, so it's not all that high permeability in the vertical anyway. And then the brown area is where it's been excavated down to the Prairie du Chien, and that's where you have the chain of lakes.
That's what we infamously call the buried.
It's a buried
river valley.
Yeah, it's a buried bedrock valley or something like that.
Yeah, and I've heard it referred to as the precursor of the Mississippi. Is that?
Yeah, that's what I would guess. I would think that that might be exactly what it is, but I'm not knowing the glacial, the past history, because Mississippi actually is right here. Yeah. Okay, running along there, so it could have been that it was in a different channel, and maybe it wasn't. Well, it was something different than the Mississippi, possibly. But so that's a bedrock valley, as I indicate here, and here I tried to on the slide, the handout. This shows this diagram, so you can actually get a profile view along a cross section what that looks like. So you can see the Platteville is present in many places, but here where the bedrock valley is, it's been excavated well through that and through the sandstone. So you got basically a window in the bottom of the aquifer through which water can leak out of the aquifer, the superficial aquifer. It was interesting in Wikipedia, I pulled this off of there, and they were actually talking about Minnehaha Falls, or Minnehaha Park. And so you can see the Platteville limestone, and then the Glenwood Shale is underneath that, and then St. Peter is below that. And the Platteville is fractured. The Glenwood Shale should be unfractured, so it should provide a impermeable boundary so that water can't go down. But wherever it's been excavated away, then you would actually have a window of opportunity for flow. This also then illustrates some GIS layers that image of the surface with the creek, and then this blue would be the superficial aquifer water table from Bob Tipping's study from the Minnesota Geological Survey. And then below that is the bedrock aquifers, and you can see the excavation that has occurred along that bedrock valley and so forth. And as you get over towards Minnehaha Falls, Coldwater Spring is over here. That was a thing, a big issue back when we were putting in the light rail and all that, because they were concerned near where the Bureau of Mines and the office used to be. So there's a deeper water table or piezometric level that exists within this bedrock aquifer. So you've got a water system within the bedrock aquifer. You've got the superficial aquifer on top of that. Those are kind of pulled away from each other as far as scale, just so you can actually see them. And so if we take a profile view of the creek, this illustrates the profile view by that blue line. That's the bottom, let's say the bottom of Minnehaha Creek. This is the location of the Brownsdale Dam right here. And we can see that the superficial aquifer water table is that black broken line, and the deeper aquifer piezometric pressure level is this blue broken line. And then the bedrock interface is given by this kind of a greenish line. Mississippi River location is right here. The elevation of the Mississippi River is over here. So you can see that the water is being drawn down because of the Mississippi River for one thing, but I'll show also that it might be because of pumping. But what we can see here is that the water table is below the base of the creek in that lower portion, and so this would explain why the upper part of the watershed is gaining and the lower part of the watershed is not gaining. It's actually losing water because the water table is below the creek. And so here, going back to that same concept that I had before, just to remind you, we've got the flow going into the creek, which is a very small fraction. A large portion of the flow being lost, and we're saying that it's being lost through that window. That window is only the excavated area that's exposing the St. Peter sandstone and the Prairie du Chien. It's about 39% of the watershed. And it's only that small portion that actually goes down to the Prairie du Chien that I believe is really leading to a lot of water loss out of the system, and that's, I believe, about 19% of the watershed. So the net recharge of the superficial aquifer, as I've said, is 6.7 inches. It's estimated to be that. And then we're saying that a large portion of that is being lost through the bottom of the aquifer, and probably mostly where you have that bedrock valley existing. So the question is, well, is the difference between the 6.7 inches and the actual flow, the groundwater that's coming out of the creek, which is about 0.3 of an inch per year, that difference is 6.4 inches. Is it being lost to the deeper aquifer? So we investigated that, and we just used Darcy's law, simple equation that says the discharge, and here we were doing this on a pixel basis, so you got these little squares. Each square has a certain hydraulic conductivity associated with it, and it has a water level, the upper water table, and the deeper piezometric level. Take the difference between those two, multiply it by the hydraulic conductivity times the area of the pixel, add them all up, and that'll tell you the total flow that's going down. And of course, over much of the watershed where you do that, very little is being lost because you got Platteville and Glenwood Shale. They don't let very much water go through. But where the bedrock valley is, lots going through. The hydraulic connectivities are hard to estimate, but they were estimated by Bob Tipping using tracer analysis, which is the best way to do that. And so we used his numbers to come up with those hydraulic connectivity values. And the conclusion was, I just wanted to show on here, this is just along the profile of the creek, but that difference in head pressure is just this. And we did this for every little area within the watershed. So you look at the whole watershed, and it's made up of a bunch of little squares. You do that calculation for every square and add them all up. And so the conclusion was is that that 6.4 inches can be made up based on that, you doing that calculation, which I found, it's not exactly 6.4, but it's very close to that. We're still working on redoing that just to confirm that, because I think it's an important part of the overall issue. Yeah. How big are they? You had to ask that. I've forgotten. These were ones that were provided by the Met Council because they had all the aquifer properties and all that for the Metro model. And I don't remember how large those grid cells were. They might be 300 foot by 300 foot, something like that. But I don't take me at my word on it because I don't remember how large they were. Yeah, they have the whole thing for the 7-county metro, and we just took out the part that has to do with the Minnehaha Creek itself.
Is that an available raster layer then for Met Council?
Yeah. Yeah, we just downloaded that, and then we were able to, we could illustrate it in the GIS, in ArcGIS, but also we're able to put it into a format. We're able to do the calculations. Basically the difference in the heads. So we had the water levels at the two levels, and we were able to calculate for every grid cell what that difference is and what the distance between those 2 points are. And then, of course, we had the hydraulic connectivity based on Bob Tipping's study. And he was using tracers to verify his hydraulic connectivity values. So what causes the deep percolation? Is it just base level control by the Mississippi, because the Mississippi's way down here, and the land surface and the aquifers are way up here. So you expect water flows downhill, it's going to go down there, right? That'd be one thing. The other possibility would be pumping from bedrock aquifers. So we'll just look at that here in a moment. So this would be the thing I'm talking about as far as base level control, and this is something we're still working on to do a little bit more analysis on this. But you can see here that, of course, because of the level of Mississippi, the water table is being drawn down just naturally because of that condition. So it could be that that's the whole main issue, is that water's coming down here, it's being drawn down because of the control by the water level in the Mississippi. Of course, the flows could be down something like this through that bedrock valley into going into the Mississippi. in the deeper aquifer that would be connected to the Mississippi. And these are things that I still need to analyze. Right now, we're just working with these rough numbers that we have. The other possibility would be some wells, of course, municipal wells that are in either Prairie du Chien or in the sandstone. There are wells in the St. Peter, there's wells in the Platteville, there's wells in the superficial aquifer. But the ones that are big production wells are the ones down in here, and I just put one in here. So the question is some of this coming in here actually going towards that well and providing a large portion of the flow that's coming out of those wells? And
How far away would those wells have to be?
Well,
How close would they have to be?
yeah, what their zone of influence is, I don't know. That would be something that we will be looking at to try to confirm some of this. So these are the size of these circles, are the magnitude of the amount of water that's being drawn out. The color has to do with which aquifer they're in. So the orange ones are Prairie du Chien. Doesn't show anything for the Jordan, but then Mount Simon and multiple levels that they're pumping from. The green is from the Quaternary, that is the superficial aquifer material. And these are the pumping rates. So I took all those that are at different levels and I quantified those in terms of total equivalent depth of water that would be removed from the watershed. And those numbers come out between 4.1 and 8.5 inches a year. So that's well over the amount, or very close to what would account for the losses that we're seeing. I'm not saying that's necessarily it. That's something that still need to confirm. Like, could be the base level control from Mississippi, could be because, partly because of this, might be a mixture of the two. So Bob Tipping also did studies on tritium concentration in the groundwater within the 7-county metro area. And what's shown here is, again, for Minnehaha Creek, these would be the locations where you've got the bedrock valley, and the pink area here would be the Prairie du Chien, the blue would be the St. Peter sandstone. And the color for these circles indicates whether or not it's old water or new water. And what we can see here is that the old water wells in the Jordan and the St. Peter sandstone are the ones that are up gradient from where the bedrock valley is. And the ones that are closer to the bedrock valley actually have a tritium signature, which would indicate it's newer water. So that would be an indication that you're not just getting water from the deeper aquifer, you're getting it from the superficial aquifer as well. That's not the entire story, but at least presenting this to some others, like Bob Tipping, they seem to agree with our conclusion about that. But I shouldn't speak for them. They have to actually look at it in more detail probably before they would completely agree with this. But it does provide some evidence that this might be occurring. The other thing that we wanted to look at was the effect of stormwater infrastructure. And of course, this is a map showing all the stormwater infrastructure in the watershed. So you know, when you see one of these pipes coming into the creek, well, it's probably being fed by this network. But there is one large pipe that's about 80 feet down that goes along the Highway 35W along that pathway. And there was a study done to look at how the condition, you know, maintenance of that. And this is just a view down that pipe, and you can see water squirting in. Well, that's groundwater coming into the pipe, and of course that water is being run directly into the Mississippi up near I-94. The water level's right here on his boots. We got
along 35W does that go?
North of the creek.
yeah.
How far north of the creek? Yeah.
I mean, where is it relative to where the creek is?
Yeah.
Or that I don't know. It goes up to here, but I don't know where right here. You know, whether it goes under the creek, that's something I don't know.
Not going to the creek.
But flow into the pipe, whereas as well as maybe flow along the pipe and along the outside of the pipe, because you basically made a conduit for the flow, could be an impact. Now, measurements of flow and maybe 1,000 gallons a minute or something like that, so that doesn't get you very far as total amount of water in a day. I mean, it's not very many cubic feet per second that we're talking about. 1.5 cubic feet per second, 1 million gallons per day. So it's not going to account for a lot, but it's one of the things that we could look at as being a possible loss of water from the system. So the conclusions are that groundwater contributions in Minnehaha Creek are in the range of 0.25 to 0.3 inches per year, and that's been corroborated with an isotope study, the seepage meter, and temperature profile measurements. What appears to be the affected area, the superficial aquifer contributing to the creek, is about 5% of the watershed area. That's based on that hydrologic system analysis that we did. And then possible causes for low water, groundwater contribution are leakage from the superficial aquifer to the underlying bedrock aquifer. Whether that's caused by pumping, we don't know. Whether it's caused by the base level control by the Mississippi River, we don't know, how to divide between those two, but that's something that still needs to be looked at. Possible leakage to the stormwater infrastructure is another option, but again, like I say, that appears to be a fairly small overall component. So most of it would be because of either pumping or Mississippi River control, or the combination of the two.
For the possible leakage to storm sewer infrastructure, it would also be to sanitary sewer infrastructure?
That would be fairly shallow. Well, no, that could be very deep, right? Yeah, that's definitely a possibility, but we didn't look at that at all. Yeah.
There is an interceptor that runs more or less along the creek.
Mm-hmm. Yeah, wherever it would be below the water table, and in many cases they are, right? So, I mean, a lot of the stormwater infrastructure is very shallow, right? It doesn't have to be deep, but absolutely, and we didn't actually look at that, so that's another possibility. All right, so just some special thanks to some different people that worked on the project. Thanks to the U.S. Geological Survey that helped us out to, lending us some of their equipment like seepage meters and also temperature probes. And then, of course, thanks to the Minnehaha Creek Watershed District and Mississippi Watershed Management Organization for support on the project. So, thank you. Yeah.
If you have time, could you talk about next steps, and could you talk about what you won't get to that you would hope would happen in the future?
Yeah, well, one of the things that we originally thought we would do on the project, and we changed the scope after we got into it a little bit, was to do some modeling work. Maybe with the Metro Council model or the Metro model, but that's something that I think would be useful to do, to look at the groundwater pumping issue, more detailed analysis of that. Instead, what we still are working on, we have until the end of March to complete the remainder of the work. Even though we have a final report draft already out and it's being reviewed by the districts, we are verifying a lot of our numbers, and we're going to do some fairly simple modeling work. I think that large-scale modeling work with the Met Council or the Metro model would be very useful, especially if we want to look at the effect of the base level control by the Mississippi River and also possible effects of pumping. I think those are the unknowns that we have right now for this. One really nice thing about the Metro model is that it's large scale, so it goes beyond the boundaries of Minnehaha Creek. Next steps would be also to, what we'd like to do is, if the district is interested in continuing with this, would be to establish some sites where we can try out the implementation of infiltration and to see how effective they are. So we got a little bit started on this with the help from the district. We didn't have to spend any of our money on it. They put in some monitoring wells down by Utley Park. Utley, just off of Highway 100. We put in, just below the Brownsdale Dam, put in 3 deep wells there. And this would be a site where we could put in some infiltration capabilities, infiltration galleries to infiltrate water, to try to see how effective that would be. You put tracer into the water and you see how much of it actually comes back into the creek.
Would you necessarily recommend infiltrating in the upper part of the lower, knowing that it's going to get lost in the lower part of the lower anyway?
Well, anything that you put in, as long as it enters into the creek and doesn't just go straight down to the deeper aquifer, it may get lost as it goes down, but you've still added something to the creek. I mean, we recognize the issue about, it's a losing creek, but the more you put into it, the more actually is going to end up ending up at high water or at the falls.
But in order to get it to the creek at all,
yeah,
you would maybe do it farther upstream.
Yeah, I mean that would be, you'd be more guaranteed to get more of it in, but I'm not sure.
Further downstream, 95% might get lost. Further upstream,
right.
5% might get lost.
Yeah, you could see from that profile that I drew up there, you'd have to put a lot of water in just to get the water table come up high enough to have that water enter into the creek, even if you're right in the riparian area. So you're better off upstream doing it. So we do also have one at a site we call the Lati wetland. There's a street called Lati Place or something like that. That's just off of the creek, and there's a bunch of wetlands there. So we put some piezometers in there, getting ready to, I mean, it's part of our study, but also it'd be a site where we could put stormwater, and try to see if it will come into the creek, make its way to the creek. So I think those would be the next steps that could be worked on. The Watershed District is already doing things with remeandering of many places, and there's sites where they're already putting stormwater into ponds that are within the meanders. And that was done prior to us even starting this study. So those would be locations possibly where we could now, if they're already set, we could start to go in and put tracers in to see how effective they are at getting water into the creek. Mike?
If you start infiltrating stormwater and you're losing a lot of that to the prairie shade, any water quality concerns?
Yeah, that might be an issue, yes. If it's stormwater that you're capturing and it's not clean, we'd need to see whether or not what's being removed by the soil, because you wouldn't want to put it in deep to start with. You'd want to infiltrate it in through soil. That would remove any heavy metals, total, hydrocarbons, other things that you find in stormwater. And we are just completing a final report for the Met Council on 3 sites where we were looking at how much of the stuff actually gets to deep in the profile. One's at Beacon Bluff site down in St. Paul. One's along Hamlin Avenue, right on Como, near Como Park. There's a large rain garden there. And then there's one on what we call the sheep's pasture right at the university, where we put in probes or samplers deep in the profile. We're collecting water samples. We've done analysis for nitrates, chloride, phosphorus, cadmium, nickel, lead, total hydrocarbons. And that report is we got in draft form right now. So that gives an indication. I mean, the concern there was, well, we put all these stormwater infiltration facilities in, what happens that we contaminating the groundwater in the long term? And that's exactly the question you're asking.
How deep are you looking at those 2 sites?
Well, at the Como Park and at the sheep's pasture, those are the deepest probes are about 5 feet.
Oh.
If it gets past there, it's not going to stop. It's going to keep going. And we put those in at the Beacon Bluff. Those were put in by the city of St. Paul. There's a big, they removed some industry or manufacturing. They're made into a green area, and they put in this big infiltration gallery, and those go down 30 feet. So they've got collectors at very large depth. at various depths, and I think one's at 7 feet, 12 feet, so forth. I don't recall the exact depths of those right now, but there's a number of these collectors, and we've got they're connected to a well, so you can just or a pipe that you can go down and measure the water level as well as collect water samples. So we did that, and we measured for a number of different heavy metals, and we looked at total hydrocarbon there, chloride, nitrate, and phosphorus.
Have you seen the data?
Yeah. Yeah, the numbers for the heavy metals are not above the standard. The total hydrocarbon might be an issue. Yeah.
I have two questions. Is your presentation available online somewhere?
This one, I also gave this, it was one that I doctored up afterwards, that was done for the Water Resource Science seminar on the university campus. So if you go to the Water Resource Center website at the university, and then they have the Water Resource Science Graduate Seminar Series. I did this in November. And so it's basically the same presentation, but here I added a few more things to it. So if anybody can go in there, they have a link, and you just click on it, and it'll open up the presentation for you. But you'll have it from here as well.
One other question. If you look at the profile along the creek, which basically shows that the water table is below the level of the creek.
Mm-hmm.
Okay. Is it even possible, with stormwater, when it rains, basically everything in the Minneapolis area goes right to the creek, except for a few rain gardens.
Mm-hmm.
Is it even possible to capture enough of that water in rain gardens, etc., to raise the groundwater level so it's actually above the
I think if you do it right near the creek, you would raise it above the level of the creek, even if that profile shows that it's below the creek. So you put water in there fast enough, it will raise it above the creek. It may not be a very long event. After you put it in, it'll continue to drain deeply, but also you would have some flow coming in. It's a question of time. How fast is it going to come in? And so that's definitely, we don't want to put it in where you might put a rain garden at somebody's lawn. If they're half a mile away from the creek, it's never going to get to the creek. So you need to do this near the creek. That's what our conclusion was. Yeah, right. Yeah. That of course is an issue. So.
I think we're just a little over time, so
Yeah.
I appreciate you coming.
Thank you very much.
And if you have questions, you're available to answer them.
Yep. I'll wait around if somebody wants to ask.
What about the vicinity of the lakes?
What about the vicinity? What about you mean what?